Last week in the magnetism topic, we learnt about the force on a current carrying wire. And I said at the time that it wasn't fundamental, the magnetism force, in the way that the electric force or the gravitational force are considered to be fundamental forces. The magnetism is a consequence of what happens when electric charges interact with each other through the electric field, but it's when one of them's moving. And you'll have seen those videos that I left you watching that to a certain extent this can be explained using some really quite advanced physics like special relativity, where in that video you met the idea that if the charges are moving, then there will be length contraction effects that take place, which mean that the wire that appears to be neutral when you are stationary with respect to the wire becomes a charged wire overall when you're moving with respect to the wire, which is quite a cool idea and indicates to you just how intermeshed all of the different ideas in physics are. However, there is a more fundamental reason why that F equals BIL force isn't a fundamental force, and that's because it's not really the wire that is experiencing the force. It's each of the charged particles within the wire that is experiencing the force. So we can go one level deeper than the F equals BIL force to ask what is the immediate origin of that force. So here we go. Okay, so here is a lone charge particle. As you know, by convention, we always refer to the forces on positive charges when we're dealing with things from a fundamental perspective, and then we just reverse the directions for negative charges. So here's a positive charge. It's moving in from the left-hand side of the screen, and it's about to encounter a region of magnetic field. Remember, these little dots in circles are our diagrammatic representation of magnetic field lines that are sticking out of the screen towards you, like an arrowhead coming towards you. And the spacing of these lines indicates that it's a uniform field, so that the strength of the fields, the magnetic field strength, is the same at all places. So what will happen to this charged particle? Well, bizarrely, it does this. It actually gets kicked off to the side. So it's trying to move left-right, but it experiences a force that you might think is vertically downwards, and you might think that that gray dashed trace is indicating a parabola shape. And so this is kind of just like the electric force or just like the gravitational force, but it's more complicated than that. In actual fact, the force that's experiencing is indeed vertically downwards at that point in its motion, but as it moves around, what we actually find is that the force changes with the location of the charge. And in actual fact, the force is always at right angles to the velocity. This is quite an odd force then, that it's always linked to the velocity of the charged particle. But as we met in those videos that I left you with last week, it is a motion effect, and therefore as a motion effect, of course, it is going to be linked to the velocity. It's just unfamiliar to us because we haven't met any other forces that have a velocity dependence to them. Drag isn't really a fundamental force, is it? So what's ultimately the issue is that it's a special relativistic effect, as we saw in the video, that the moving charge experiences the world in a slightly length contracted way. And that means that things that used to be electrically neutral can suddenly become charged, and this can push them away. However, as A-level students, we don't need to worry about that. We just need to learn the rule. And the rule is that the force has experimentally been determined to be at right angles to the velocity at all points during the charge's motion. So we can do something similar to what we did with the wire, and we can draw a pair of axes. And we can talk about the fact that if the magnetic field is pointing in one direction, even if the charged particle isn't moving exactly at right angles as drawn, there will always be a component of velocity that's at right angles to the field, unless it's truly parallel. And so there is the B field in one direction, there's whatever component of velocity that's perpendicular to that, and then perpendicular to both of those things will be the force. And this is very similar to what we did for the wire with the BIL force, and you can use your same hand for doing this. Now, you will see in some textbooks that they offer you the opportunity to learn yet another rule with your hands. To do this, there's a rule where you can use the palm of your hand and have something sticking out the palm of your hand and your fingers pointing in another direction and your thumb. I just find it very confusing. We've already got one rule that works well enough. I'm just going to recycle it. So by all means, embrace the other hand rule suggestions that you might find in revision guides, textbooks, videos, but I'm just going to stick with the one rule that we already know, and I'm just going to recycle it. So the idea here is that you would again take your left hand, move your fingers and your thumb into a right angle configuration. First finger field goes in the direction of B. Now current is the direction that positive charge flows in. So you just need to point your middle finger in the direction of the velocity component. Just remembering that a current is a flow of positive charge. And so if it happened to be a negative charge, you would have to point your middle finger in the opposite direction to what the charge is flowing in, because if the positive charge is flowing one way, then negative charge would be flowing the other way. So you have to reverse your finger for negative charges. Don't snap your finger, that would be bad. Rotate your whole hand. And then your thumb will be pointing in the direction of the thrust or the motion, the force. So same right hand rule as we used for BIL. With the component of the velocity that's perpendicular to the B field being the analogy with the I sine theta component of the current that was perpendicular to the field when we had the wire. And then here's for the force law. So it has been experimentally determined that the force is directly proportional to the charge on the particle, double the charge, double the force, directly proportional to the speed of the particle, double the speed, double the force, and directly proportional to the magnetic field strength. Double the magnetic field strength, double the size of the force. And I said to you last lesson that you could think of F equals BIL as kind of an analogy to the F equals QE or the F equals mg force, but it's really this one. You can see there that this force is just begging to be F equals QB, like F equals QE. It's just there's this V term in the middle of it. It doesn't work if the velocity isn't there. I suppose you could argue that for a particle traveling at 1 meter per second, then the force law becomes F equals QB, but there's still that 1 meter per second hovering around that's changed the units. And so this is just a strange force. It's a velocity dependent force. And as I said, the reason that it appears to be a strange force is because it's not fundamental. It's our way of mathematicizing what's happening to the electric force for moving particles without getting bogged down with too much mathematics. In effect, we've invented the magnetic field to interact with the charged particles when they're moving. You can do this without the B field. It's just the maths becomes very, very confusing. So it makes a conceptual sense to imagine that there is a magnetic field that's controlling the particles. Mathematically, you can do away with it, but we're going to keep it because it's something we can visualize and think more clearly using. So for any charged particle moving in a magnetic field, it will experience a force equal to QVB or BQV or QBV, whichever way around you want to write it. That is perpendicular to both the magnetic field and the velocity. Just bear in mind that that V is the component of the velocity that is perpendicular to the field, and therefore if the V truly is parallel to B, there won't be a perpendicular component and the force won't exist. Given that the deeper level of understanding here is that each charged particle separately experiences a force while moving, then we can now add up all of the forces on all of the charged particles to work out the overall force on a wire. So you should be able to do this. So here's a little tiny section of wire, and it's got loads of electrons moving inside it. And those electrons have an average velocity of v along the wire. And then if we place the wire in a magnetic field, then because the charged particles are moving in a magnetic field, every single one of those charged particles separately will experiencing a tiny little force F. And if you just use your left hand now, just to play the game, you need to push your first finger in the direction of the blue arrow. And then you're tempted to put your middle finger in the direction of the green arrow until you remember these are electrons. And so as electrons, you need to point your middle finger in the opposite direction to V because they're negatively charged. And when you do that with my hand contorting into some horrible shape in front of you, breaking my wrist, your thumb ends up pointing in an upwards direction. And what is the size on each one of those electrons? Well, it's the QVB, but the charge this time is the elementary charge E. And you remember that's very, very small. And the velocity isn't very big either. So the E times the V is not a very big number. And the B is only ever going to be, 1 or 2 Tesla, absolute most. The magnet that I showed you in school when we did the BIL experiment was 0.2 Tesla. So none of those numbers are going to add up to a very big force. And that's because these are electrons and they don't have very much charge. However, there are a lot of them. If you remember that there can be 10 to the 29 free electrons in a conductor, and therefore, no matter how small the EVB is, we can scale this up to an enormous number just simply by the number of electrons. So how many electrons are there? Well, if you cast your mind back to what we did on electric current in year 12, we remember that the number density is the number of free electrons per meter cubed. And then if we multiply that by the volume of the wire that we're interested in, we'll get the total number of electrons. So what is the volume of the wire? It's the cross-sectional area A multiplied by the length of the cylinder that's in the field. So the wire can be as long as you want, but only a bit of it is going to be actually experiencing the magnetic field, and therefore only those electrons are going to be experiencing a magnetic force. Any of the electrons that are in the part of the wire that are not within the B region are not going to experience the force. So the number of electrons that are in the field is the volume of the cylinder, A times L, multiplied by the number density of the electrons inside it. So we just need to multiply the number of electrons by the force on each electron to get the total force, which is a big string of algebraic letters. So if we just order them into the right sequence, hopefully you'll recognize them. So if we just collect up the N, A, the V, and the E, stick a B on the front and an L on the end, you can hopefully see where we're heading with this. We just need to note that although some electrons will be traveling slightly faster and some electrons will be traveling slightly slower, on average, their speed will be the drift velocity. And so take the V as the drift velocity, then they'll all have the average force. And so we can just sum them all up and recognize NAVE as the current. That derivation in an ordinary year is examinable, so please make sure that you can do it. Okay, so that's linking this semi-fundamental BQV force on every single moving charged particle, scaling it up to produce what we met last lesson, which was the measurable force on a current carrying wire. So that was one thing that I wanted to do with you today. The other thing that I wanted you to do today is meet the link to circular motion. So hopefully when you saw that picture, you should have thought to yourself, you know what, I've seen pictures like that before, maybe not with the blue circles in the background, but you've certainly seen a particle moving with a force perpendicular to its velocity. And so hopefully you were already thinking about circular motion before I raised it with you. And so we can do a circular motion analysis of this. We always start with F equals ma, and then we remember that our F is the magnetic force, so that's this QVB, and our acceleration for particles moving in circular motion is v squared over r. And you can see that one of those v's cancels on each side, and then we can rearrange it to make r the subject. And what this is telling us is that the radius of the circle will be constant, and it will depend on 4 factors: the velocity of the particle, the mass of the particle, and the charge of the particle, and then the strength of the external field. So let's fix the external field and ask, what can the charge do to make a difference to how it moves? So you should be aware of the fact that charged particles moving in a magnetic field will form very tight circles with a small radius if they have a very, very small mass, or if their charge is very high, and also if their speed is very fast. Oh, that should say, yeah, that should say slow. Their speed, if their speed is slow. So we can use this to identify particles, actually. So we talked a little bit when we did the nuclear physics topic back in the summer that a cloud chamber is a device that allows us to see the vapor trail of particles moving through a supersaturated gas, and we can actually see that grey dashed lines as a little vapor trail in cloud chambers. And if we attach a magnetic field to the cloud chamber, then as particles travel through the cloud chamber, they will arc, and from the rate we can take photographs of that, and then from the radius of the circle that the arc is part of, we can work out maybe which particle it is. If it swerves one way, it'll be positively charged, as in the diagram. If it's negatively charged, the force will be in the other direction, so it'll swerve upwards, as the diagram is on the screen. Also, the mass of the particle will make the radius change. So the tightest circles will be the lightest particles, possibly. And so we can use the radius of the particle track in a cloud chamber to try to identify which particles we're dealing with. However, why stop at a cloud chamber, which is a difficult machine to make every time you want to use it, and take photographs and do it all manually? Why not make a machine that can do this? So we can do that, and it relies on us identifying the mass to charge ratio from the radius. So if we fix the velocity and we fix the magnetic field, then we can measure the radius, or use a machine to measure the radius, and that will give us the mass to charge ratio of the unknown particle. And this is done on a large scale in machines that chemists use all the time, called mass spectrometers. And if you're a chemistry student, no doubt you have studied this. I'm only going to brush against it briefly now. There's a little bit more detail in the physics textbook, but there'll be not near as much detail as you do in chemistry. A brief bit about how this machine works. This is one of the main methods that chemists use to identify unknown substances. So you take a small amount of the substance and you heat it up so that it becomes dissociated from its electrons, so that we've got ions. And then because they're charged ions, we can use an electric field to accelerate those ions and let them pass out through the electric field as a beam. And we met this for accelerated electrons in the electron gun, but it doesn't have to just be electrons. It can be any charged particles. Once we have a source of accelerated charged particles, we then need to understand that they are all going to be traveling at different speeds, depending on how they came to be accelerated. So we just need to use a device called the velocity selector, which only allows some of the charged particles to become our beam, because if we're going to identify the mass to charge ratio, we need to have fixed the velocity of the particles to a known value, and that's what the velocity selector does. More on that in a second. Then we've got a region of magnetic field that's going to do the curving and is going to make the particles change direction. And then we just need to detect where they went from. And by placing the detector at different locations, the location of the detector will allow us to determine the radius of the curvature of the path of the beam. So there goes the beam. You can see in the velocity selector that particles that have the wrong velocity hit the walls of the velocity selector and don't make it through the aperture at the end. So what's going on inside the velocity selector? We use an electric field vertically downwards to push the positive charges downwards and the negative charges upwards. But then to give some of them a straight line through the detector, we then apply another magnetic field to the velocity selector so that the magnetic force is in the opposite direction. So the positive charges that were being pushed downwards will get pushed upwards by the magnetic field, and the negative charges that were being pushed upwards will get pushed downwards by the magnetic field. And if we want the particles to go straight through, we just need those forces to be balanced. So we want the QE force downwards to equal the QVB force upwards. So the Q's cancel out in that formula. It doesn't matter what charges the particles have, and there's no masses in this formula, so it doesn't matter what the mass or the charge of the particles is. It just depends on the speed. So we've got this formula that the electric field downwards is equal to the velocity times the magnetic field strength upwards. And so if we just tweak our E and our B to be just the way we want them to be, you can see that V is just E over B. So if we just take our ratio of the electric field strength and the magnetic field strength to equal the velocity that we want, then we can know what speed the particles are coming out at. And we can change the speed if we want to by just tweaking E and B. And this allows us to know the speed of the particles that come out of the accelerator and the velocity selector. And then, like I said, the location of the detector allows us to determine the radius of that path. And from that radius, and the velocity and the B field, we then get the mass to charge ratio of our unknown substance. And we probably, if we were maybe doing some forensic science, we probably know the origin of the unknown substance. We might suspect, for instance, that it's some paint from a car bumper or something like that. So we probably have a suspicion of what the chemical is in the first place. So then we can compare the mass to charge ratio with a whole tabulated data set of known mass to charge ratios of known substances. And then if there is a gray zone where it could have been, you know, this or this or this, we can say, well, it's probably a component of paint or whatever, and therefore it's most likely to be this chemical here. So mass spectrometers are commonly used for identifying unknown substances, or sometimes even when you know roughly what substances you've got, you might want to work out the relative abundance of different substances. So you could use the magnetic field or the velocity selector to collect the entire mass to charge ratio of a particular radius, and you can weigh what you get so that you know how much of it you got, and then you can collect all of the other substances as well that might be in a mixed sample, and then you can work out the relative abundances of different chemicals. And then from the relative abundances of lots and lots of different chemicals, it might be that you can identify not just that the paint was, for instance, blue, but you might be able to pin down the manufacturer of the paint, or maybe even the batch of the paint, and therefore which shop sold it. And therefore, again, from a forensics point of view, you might be able to then go obtain the CCTV and see which customers bought that batch of paint from those shops, and therefore maybe identify your suspect that way. So lots and lots of use with lab chemists and also forensics. So that's the mass spectrometer. Like I said, if you're a chemistry student, you'll have done lots on this. If you're not a chemistry student, there's a little bit of more information in the textbook if you would like to know it. However, we are halfway through the lesson, and I wanted to stop there because I'm quite keen for you to use the other half of this lesson to just skim read the notes in the textbook and to do the questions that are at the end of the textbook chapter.